Welcome to the virtual lecture on Chapter 2, The Chemical Basis of Life, Part 2. To recap, the first type of chemical bond that we covered in Part 1, I would like to take you through the drawing of a water molecule a second time. Remember, water is a great example of a specific type of covalent bond, that being a polar covalent bond. We learned how to draw a water molecule in two different ways. The first, as you can see here, an electron distribution diagram. And we also learned a more simplified depiction of a molecule, that being the structural formula. So let's review by drawing the structural formula of water a second time. So remember, we just write the chemical symbols, so oxygen, and then we have two hydrogens, and we use solid lines to depict the two covalent bonds. Just like that. That's water. And remember, since this is a classic example of a polar covalent bond, and really the only example of a polar covalent bond that you need to be able to recognize, there's an unequal sharing of electrons. And remember that creates partial charges, or poles of charge, on the water molecule itself. So lastly, let's depict those regions of electrical charge. Remember, since the electrons are spending more time near oxygen, it's going to be partially negatively charged. And the hydrogens will be partially positive. I also want to point out that the first example of a molecule that I gave you in Part 1 was hydrogen gas, hydrogen to hydrogen. And I want to be clear that that was an example of a non-polar covalent bond. Even though I hadn't yet covered them, the reason I picked that example was just to give you a simple molecule for our first molecule to draw. But that was not a polar covalent bond. So now we're ready to move into the second type of covalent bond, and those are the non-polar covalent bonds. And the key word here is that electrons are shared equally between the two atoms. Okay, so it's an even tug of war between the two participating atoms. And therefore, since the two electrons are split right down the middle, there are no regions of electrical charge. So the two atoms are neutral. And there are two conditions under which a non-polar covalent bond may exist. The first being if you have a covalent bond between two of the same element. For instance, carbon sharing a pair of electrons with carbon, or oxygen to oxygen. Those are always going to be non-polar covalent bonds because the two atoms are the same, and therefore they have the same pull or the same affinity for electrons. So it's always going to be a perfect share. Beyond that, the only other example of a non-polar covalent bond that you need to be able to recognize is whenever you have carbon sharing a pair of electrons with hydrogen. Now, carbon likes electrons a little bit more, but the difference in affinity for electrons between the two atoms is negligible. So the pair of electrons is shared relatively evenly. And again, that makes it so that both atoms are electrically neutral. There is no charge. And down here at the bottom, let's go through one more example of drawing both the electron distribution diagram and the structural formula for a molecule. In this case, we're going to draw oxygen gas. And the molecular formula for oxygen gas is just two oxygen atoms, so it's O2. And the first thing we want to do here is fill the shells of the 2 oxygen atoms with electrons. So oxygen, which is atomic number 8, has 8 electrons. So we're going to do the same for both. This is good practice. Remember, the first shell has 2 electrons. Then we move to the second shell, 3, 7, all the way until we get to number 8. And you can notice that oxygen just needs 2 more electrons to have a full valence shell. So oxygen has the tendency to form 2 covalent bonds to help it attain that valence, that full valence shell, that octet. Now, I'm going to go back here. What I should have done, just to make this easier to draw, is I'm going to draw the 2 unpaired electrons on the right side. So I'm going to draw it like this, just so I can easily show the covalent bonds. So same idea. There's 2 unpaired electrons. I'm going to do the same thing with another oxygen atom. Remember, the key is to put an electron at each of the 4 corners prior to pairing them. But once you pair them, it doesn't matter how you pair them. So there's the 8 electrons. We have 2 spots or vacancies that oxygen is looking to fill, and 2 oxygen atoms, if they come into close proximity with one another, can help each other fill each of their 2 electron vacancies. So the last thing I'm going to do is I'm going to show that they're going to come close to one another, and they're actually going to do just that. They're going to share That's okay if it's a box. I was going for a circle, but there we go. The rectangle and the oval represent the 2 shared pairs of electrons. So that is why we write out oxygen gas like this. Not with 1 line, but with 2. Because the 2 oxygen atoms actually share 2 pairs of electrons. Now I'm just drawing this to give you an example of a non-polar covalent bond. So notice that it's 2 of the same atom. They're both oxygen. So they're going to share each pair of electrons equally, meaning that it is a non-polar covalent bond. Now, the next term we're going to cover is something called a hydrogen bond. And the first thing that I want to say about hydrogen bonds is try to think of them as hydrogen interactions. Okay, they're not bonds in the traditional sense of the word. It has nothing to do with an atom striving to attain an octet. So it has nothing to do with sharing electrons or transferring electrons. Okay, I think it's poorly named. It's basically when you have 2 molecules that have partial electrical charge, when those 2 molecules stick together. So when something that's partially positive sticks to another molecule that's partially negative, they form a hydrogen bond. Okay, so hydrogen bonds are extremely weak electrical interactions that occur between 2 different partially charged atoms. An important rule of thumb in chemistry and biochemistry is positive likes negative. So remember that. Opposites attract. And the way that we denote a hydrogen bond is a dotted line or a dashed line, as opposed to the solid line, which represents a covalent bond. And that reminds me, I want to point out that whether it's a non-polar covalent bond or a polar covalent bond, it's still always drawn with a solid line. Okay, so looking at the solid line, you can't necessarily tell if it's polar or non-polar. You have to look at the participating atoms. And again, if you see oxygen involved in this bond, you know it must be polar. And it is actually polar covalent bonds that result in the ability of a molecule or its potential to form hydrogen bonds. And as the name implies, it always involves a partially positively charged hydrogen atom sticking to something else that's partially negative. So this is another one where just reading the definition, it's confusing. You need to see it to understand it. And the best example to illustrate this, again, is water. Because water is a really special, unique molecule that has the ability to form hydrogen bonds with other water molecules. Very important property of water. So we're going to do just this at the bottom. We're going to draw out hydrogen bonds as they form between liquid water molecules. And moving forward now, we're just going to use the structural formula, and we're not going to use the messier electron distribution diagrams. So the first thing we want to do is draw a single liquid water molecule. So remember, as we just did, it's got 2 hydrogens and an oxygen. And importantly, don't forget the regions of partial electrical charge, which result from the unequal sharing of the electrons within the 2 polar covalent bonds. So there's one water molecule, but let's say you're looking at a glass of water or a bottle of water. There's not just one water molecule, there's billions of water molecules, okay? I haven't said this, but atoms are really, really small. You can't even see them with a microscope, you know? In a bottle of water, there's billions, like more stars than there are in the whole galaxy. So, extremely small. So there's never just one water molecule, there's always many around each other. So I'm going to draw a second water molecule. I'm going to draw it right here. And I'm going to orient this second water molecule so that it faces the first in a certain direction. And that direction is positive likes to stick to negative. So what I'm saying is the partially positive hydrogens of one water molecule will stick and form a hydrogen bond with the partially negative oxygen atoms of other adjacent water molecules. And that is a hydrogen bond, or one example of a hydrogen bond. So on this second water molecule, I'm also going to denote the charge. So negative, positive here, positive here. I'm going to use a different color for the hydrogen bond. I guess I'll use green. And again, we denote this with a dotted line or a dashed line. I'm going to use dots. And that's our hydrogen bond. Now, a single water molecule has the potential at any one moment in time to form up to 4 different hydrogen bonds with other water molecules. So I'm going to show that. Or actually, I'll show 3 instead of 4 for the sake of time. So let's draw one more. And the third is going to be up here. Let's draw the charges. Lastly, let's draw the hydrogen bonds themselves. Okay, there are 3 hydrogen bonds now surrounding our original water molecule. Now, as we're going to learn, liquids are moving. So these molecules are not solids. They're not frozen in place. They're not just vibrating. They're moving around pretty rapidly. So all these water molecules are constantly bashing into one another, forming a hydrogen bond, moving away, forming a bond, moving away. So many times, I'm going to throw out a number here, it's pretty crazy. A single water molecule will break and reform a hydrogen bond in a trillionth of a second. So it does it like a trillion times in 1 second. That's how fast these are moving. Breaking, reforming, breaking, reforming. Each bond is transient, right? It lasts for a really small fraction of a second. But collectively, at one moment in time, the collective force of many hydrogen bonds can be very strong and very relevant to biology. For instance, it's hydrogen bonds that holds your DNA together, the 2 strands. One bond is very weak, but a whole long strand of them can hold your DNA together. So again, they're transient, meaning they don't last very long. They're weak, so it's the weakest of the 3 types of bonds that we're covering, but they have strength in numbers. So hydrogen bonds are related to how water interacts with both itself and other types of molecules. So this is a very important slide. We can classify other biologically relevant substances or molecules based off of whether they like water or they fear water. And to understand whether a substance likes or fears water, you have to go back to the electrical charge on the water molecule. And you just need to remember this simple point. Water likes and is attracted to any other substance that is also electrically charged. Okay? Because then the positive can stick to the negative and vice versa. Now, something that is not electrically charged, like it's neutral, like for instance a fat or an oil, it's not attracted to water. There's no charge to stick. So in a sense, it doesn't fear water, it just doesn't care for water, it doesn't stick to it. So it's very important to be able to break down substances based on how they behave with water. So as we're going to learn moving forward, most molecules and ions and dissolved substances in your body, inside your cells, inside your blood, most of them like water. Most biologically relevant molecules have one or more regions of electrical charge. And since they do so, they have the tendency to be attracted to and to stick to water. So we say that these molecules that have some degree of electrical charge, we say they like water. We call them water-loving. And the more technical term for that, water-loving, is hydrophilic. And it's really important that you understand that that also means that that substance that loves water can therefore be dissolved in water. So anything that can electrically stick to water can also be dissolved in water, meaning it's water soluble. So again, that represents most substances. All dissolved salts, which become ions, like for instance, sodium, chloride ions, magnesium, calcium, as we're going to learn, they're all charged. So they all like to stick to water. They're hydrophilic. they can be dissolved in water. That's why salt dissolves in water. Some other examples. Sugars. Okay, carbohydrates, a very important class of biological molecules. A hallmark of these molecules is having oxygen bound to hydrogen atoms, meaning they have polar covalent bonds, meaning they're partially electrically charged, meaning they have the tendency to stick to water. And that is why all carbohydrates, with the exception of things like cellulose, dissolve in water. Now, something that, again, is not electrically charged fears water. It's hydrophobic. And that would be a molecule that is composed of nonpolar covalent bonds. So there's no poles, there's no region of charge. The whole thing's neutral, so it doesn't stick to water. So again, these are things like fats, cholesterol, phospholipids. And since they don't stick to water, since they're hydrophobic, we say that they are water insoluble. They can't be dissolved in water. And think about it. Think like oil. Oil and water don't mix. They form two layers because they're just not attracted to one another. And that pretty much includes all fats. So, I'll say it again. Really important slide if you can understand these basic concepts here. And now we're ready for the third and final, I guess fourth. We went over polar covalent, non-polar covalent, hydrogen bond, which is not really a bond like we said, but now we're ready for ionic bonds, the type of bond that holds together salts. And this is a bond that results from the transfer of electrons. So there's no sharing involved. Basically, one atom is going to like electrons so much more than the other atom that it steals an electron from it. So there's always going to be one atom that loses an electron and one that gains a new electron. And the result are going to be atoms that become ions, that are fully charged and attracted to one another. And the resulting substance is going to be called a salt, also known as an ionic compound. This is another one where it's a lot easier for me to give you an example and then come back to this. So one of the most common examples of a salt is table salt, sodium chloride. Sodium ions involved in ionic bonds with chlorine atoms. So let's show why sodium and chlorine have the tendency to form this specific type of bond. The first thing we want to do is we want to look up sodium and chlorine. So sodium's way over here. And you can see its atomic number 11. So that means it has 11 protons and 11 electrons. So we're going to draw sodium right here at the top. So I'll have this represent our sodium atom, Na. If you're wondering where the Na comes from, some of these chemical symbols come from other languages, whether it be German or Latin. So this one is short for natrium, which means sodium. So we have 11 electrons. So I'm going to put 11 there. And I'm actually going to give myself a little bit more room. I'm going to put this at the top. All right, so some good practice. First, we're going to place the electrons into their shells. In this case, we have 11. So there's 2, 3, 4. So now we're at 6, and now we can start to pair them. 7, 8, 9, 10. We have one more to go, so now we're full in the second shell. So we actually have to draw another shell, a third shell. Might take me a few attempts to get this perfectly round. Let's see. Not bad, I'll stick with that. Number 11. And number 11 is hanging out here by itself. And I want you to look at this sodium atom and ask yourself, what is the simplest way for this sodium atom to have an octet? Is it easy for this sodium atom to gain 7 electrons? That's quite a bit of work to have a full third shell. Or is it easier just to get rid of this 1 electron in the third shell and then have a full second shell? Well, the answer is the latter. It's easiest just to get rid of this lone electron. Then sodium will be happy. But this is only half of the story. We need to take a look at the other atom that's going to participate in this ionic bond, and that atom is chlorine. And if you look up chlorine over here on the right, you'll see that it's atomic number 17, which means that it has both 17 protons and 17 electrons. So the next thing we want to do is to, I already know I'm going to need a third shell, so I'm just going to draw it now. We need to place these electrons into the shells. So I'll do this one a little bit quicker. So we're at 10. $15, $16, $17. And then ask yourself, what is the easiest way for chlorine to attain an octet? You should notice it's easiest to just gain 1 more electron. So it's really close, it just needs 1 more. Do you see how sodium and chlorine can help each other out? Sodium really wants to get rid of 1. Chlorine really wants to gain 1. So when this ionic bond is formed, there's going to be a transfer of electrons. So this electron here, I'm going to put a circle around it, is going to be transferred from sodium to chlorine. And the result was meant to be the same color blue. Oh well. The result is that now chlorine has an octet, a full third shell. And if we go back here and erase that electron, sodium has a full second shell. They're both happy, both stable. But something else happened when we transferred electrons. We now have an unequal number of electrons and protons for each of these 2 atoms. So remember way back to part 1, or the part 1 video, we said unless otherwise stated, atoms are neutral and have equal numbers of electrons and protons. Well, that is no longer the case here. Chlorine's going to have 1 more electron than it usually does. Sodium lost 1. So that's going to create atoms that have full electrical charge. They are called ions, meaning they are atoms that have unequal numbers of protons and electrons. Don't confuse that with isotopes. So the first thing we want to do is we want to calculate the electrical charge of each of the resulting ions. We'll start with sodium. So sodium has 11 protons. We'll put a P and a plus for proton. It used to have 11 electrons, but it lost one. So now it has 10 electrons. So it has one more unit of positive charge than it does negative. So if you do 11 minus 10, you get positive 1. And that is the charge of sodium now, plus 1. So we just put a plus. So now sodium has become an ion. It's electrically charged because it has an imbalance in the number of protons and electrons. Same thing with chlorine. It's always going to have 17 protons. It used to have 17 electrons, but it gained one more. So now it has one more unit of negative charge than it does positive. If you do the math, you get negative 1. So the chlorine ion has a single unit of negative charge. That is what keeps this resulting salt together. The sodium and the chlorine, not only did they make each other happy by transferring electrons, now they're electrically attracted as well. They stick strongly. And that resulting, we don't really denote it, we don't usually draw them out. The reason we don't draw them out in biology is because they don't exist in your body. Because your body is water-based, and as we're going to learn, water dissolves salts. So you never have a salt in your body, you just have the free ions floating around. But I'm going to draw like an arrow here. These two are attracted. So that is a salt. The last thing I want to do here with this picture is name the two resulting ions. Now in chemistry, the positive ion is always called the cation, and I remember that because it has the T in the center, and the T to me looks like a positive charge. So the cation is always the positive one, so that's sodium. The negatively charged ion is called the anion, and the name of it changes. It has a new suffix ending in "ide." So instead of this being called sodium chlorine, we call it sodium chloride, also known as salt. And salts are not just one sodium ion attracted to one chloride ion. It's many. Now it's always a 1-to-1 ratio, but it's a big crystal of sodium chlorine, on and on. Okay, so that's the general structure of a salt. And if you look at the periodic table, you can see that ionic bonds are usually formed between elements in the first column with those in the 7th column. Those that need to lose one and those that need to gain one. So that's why you have salts like sodium fluoride, sodium chloride or calcium chloride, magnesium chloride. There's not just one type of salt, there's many different salts. Potassium chloride, for instance. So I'm going to take you through one more example. Now this is straight from the text. We just went through the formation of table salt. Same thing I just drew. We're going to do one more example here. Pick a different salt, in this case sodium fluoride. So let's do that. And I'm going to try to keep, well, I guess I can't. I already have it set up on the bottom, so I'm going to move to the bottom half of this page. And we'll start with sodium. Again, it's atomic number 11. And then our other element is fluorine, which is atomic number 9. So sodium is going to look just like it did at the start of our last example. We have 11 electrons, so and then with fluorine, it's atomic number 9, so we have 9 electrons. And as you can see, fluorine really wants to gain just one more electron. So same as before, sodium's going to lose its lone electron. Fluorine will gain that same electron. So there's a transfer of electrons. The result will be 2 electrically attracted ions held together, aka a salt. We can calculate the charge. So sodium lost one of its 11 electrons. So now it has a net positive charge. Fluorine gained one more electron, so now it has 10. Has a net electrical charge of -1. Positive likes negative, they're going to be attracted to one another. There you go. Sodium fluoride. Now again, moving forward, covalent bonds are more important in biology because they hold together the major biomolecules that we're going to discuss: carbohydrates, proteins, lipids, and nucleic acids. Whereas again, you don't find ionic bonds in water-based solutions because water rips apart salts, leaving behind just the ions dissolved in water. So I'll say that again. Ionic bonds are not as strong as covalent bonds. So covalent are the strongest. Ionic are intermediate. Hydrogen are very weak. So ionic bonds are not very strong because water can break them. So they dissolve in water. Our next topic is pH in solutions. And pH is a measurement of how acidic or basic a water-based solution is. Now, most solutions, with the exception of certain organelles in your cells like the lysosome and certain organs like your stomach, most regions in your body are relatively neutral, meaning they have a pH in the middle of about 7 to 7.4. But what is pH? What is it a measurement of? Well, it's a measurement of a certain specific ion in a water-based solution, and that ion is something called a proton, also known as a hydrogen ion. So remember, hydrogen is a very simple element. It just has one proton and one electron, right? Atomic number 1. And all solutions to some degree have hydrogen atoms that have lost their lone electron. So here's hydrogen, there's the atomic nucleus, and it's got like one electron hanging out. Okay, I won't explain or talk about why, but solutions, like I said, to some degree, have hydrogen atoms where they've become ions and actually lost that lone electron, making it so that, in essence, it's just a proton floating around with positive charge. And pH is a measurement of the relative amounts of protons in a solution. So the scale goes from 0 to 14, 0 being the most acidic, 14 being the most basic, 7 being neutral. So when we say that a solution is more acidic, we mean that the pH value is low, like 0, 1, 2, 3, or 4. And we also mean that the concentration of protons is relatively high. So understand this relationship. The more protons in the solution, the lower the pH, the more acidic it is. The less protons in solution means a higher pH, and we call that a more basic solution. There are substances, oftentimes molecules, in life that have the ability to influence the pH of the surrounding solution. So substances that increase the amount of protons in the solution are called acids. Substances that therefore decrease the amount of protons, therefore making it more basic, are called bases. This is an important concept because the pH of a solution affects the structure and therefore the function of the molecules located in that solution. So you're composed of molecules, right? Carbs and DNA, proteins. And if you change that pH, you're going to affect the structure of the molecules, therefore affecting their function. So biological solutions are very sensitive to slight changes in pH. So I've been tossing around the word solution here, and what that is it's a liquid homogeneous mixture composed of two or more substances mixed together. And in biology, we're always talking about water-based solutions. Okay, so every solution in biology is considered an aqueous solution, which means water-based. And since it's water-based, we call water the solvent. Water dissolves the other substances. And the other substances that are dissolved within the water are known as the solutes. So in a cell, you have many solutes. You have ions like potassium and calcium, chloride ions. You have proteins, which are dissolved in the water. You have sugars and other small molecules. Those are all solutes. And our last topic is going to be about the special life-supporting properties of water. And all of these life-supporting properties that I cover draw back to the fact that water is composed of two polar covalent bonds, and therefore it's an electrically charged molecule. So all of that is due to the fact that water is charged. So our first and most important property of water is the fact that water is an excellent solvent. It's really good at dissolving a multitude of substances, like those that I just rattled off 60 seconds ago. Carbs, proteins, DNA, ions. Those are all substances, as we're going to learn, that are charged or partially charged. So that means they are hydrophilic and they can electrically stick to water. They like it. And the reason, again, that water is so great at dissolving this great variety of substances is because water is partially charged. So in a simple sense, we're just saying, yeah, water is charged and it can form hydrogen bonds with a lot of different substances. Basically, anything that's charged will form a hydrogen bond with water. So all of these are hydrophilic, water-loving substances. So here's an example. We just covered the formation of table salt, sodium chloride. Here it is. And this is showing you why water is so great at dissolving and breaking ionic bonds. So what the water does is it pulls the ions away from each other. So let's focus on the chloride ion. It's negative. Remember, water has these two regions of partially positive charge, the two hydrogens. So many water molecules are going to rip that chloride ion away from the salt and surround it so that all those hydrogens are facing it. And those are, it's not shown here, but those are a bunch of hydrogen bonds forming between the water molecules and the chloride ion. Same thing is going to happen with the sodium ion, except it will be attracted to the negatively charged oxygen. So that's what happens to a salt whenever it's placed in water. It's ripped apart into its constituent ions. That's one example. Another example, which I don't have here, but I'll come to later in the class, is sugars like glucose. Glucose, as we're going to see, has partial electrical charge, and it sticks to water in the same way. So if you stick to water, it means you have the capability of being dissolved in water. Second major property, which we actually already covered, we just didn't put a name to it. Water forms hydrogen bonds with other nearby water molecules. We actually drew that out earlier in the video. We have a name for this property of water sticking to other water molecules. We call it cohesion. Cohesion is responsible for water's high surface tension. So think about if you have like the surface of a glass of water and you poke a needle at the surface, you can apply some pressure against the surface of water until that needle head will finally burst through the surface. It's because the water is pushing back. It's like the water's holding hands and, linking arms. There's strength between the water molecules. Okay, and that strength is due to the hydrogen bonds between the water molecules. I have a picture of a redwood tree because that's how trees are able to transport water up against gravity. It's by pulling these long chains of water molecules upwards, held together by hydrogen bonds. Cohesion results in water having something called a high heat capacity, or also known as a high specific heat. And that is to say, relative to other substances, it takes a lot more energy to increase the temperature of water by 1 degree Celsius than it does other substances. So you have to apply a lot of heat, a lot of energy to increase the temperature of water. Okay, so we say water is resistant to extreme changes in temperature. So think about you're boiling water, let's say for tea, and you turn on this flame, pretty hot, over 200 degrees Fahrenheit. You have your water here sitting right on the flame. Why does it take over 5 minutes for those water molecules to become a gas and heat up and start to boil? Quite a while. Well, you're waiting for all of those hydrogen bonds that exist between the water molecules to be broken. And you have to break all of those hydrogen bonds until the water molecules are moving fast enough that they are a gas, right? And it can start to evaporate and boil. So it's those hydrogen bonds, that sticking of water to water, that explains the reason that so much heat has to be applied to water to change its temperature. And that's huge. That is responsible for phenomenons like sweating. So for instance, when you sweat, you allow the warmest water molecules to leave as a gas, meaning the water molecules that are left behind on the surface of your skin are the cooler ones. So you cool down. It's the reason why we're able to maintain a constant internal body temperature that doesn't vary. Water helps us maintain it within a very narrow range. And then it also relates to many of the weather phenomena that we covered in chapter 34. I'll just give one example. Relates to the reason that coastal regions are more moderate in temperature than inland regions. And that is because of the influence of a great body of water, which can absorb an immense amount of heat from the sun without even becoming that much hotter, therefore cooling the air directly around it. So water can store an immense amount of energy.